Imagine a world where every digital secret, every secure transaction, every private message is suddenly laid bare. This isn't science fiction. It's the potential reality posed by powerful quantum computers. These machines, once built at scale, could shatter the cryptographic foundations of our digital world. So what's the problem? Most of our current digital security relies on public key crypto systems, things like RSA and ECC. Quantum computers will be exceptionally good at breaking these. Think of it like having a master key to every digital lock currently in use. This is why the race is on to develop what we call Post-Quantum Cryptography, or PQC. PQC aims to create new cryptographic algorithms that are secure against attacks from both classical computers, like the ones we use every day, and the quantum computers of the future. It's a vital defense mechanism we're building right now. But developing these algorithms is just the first step. Getting them standardized and implemented globally is a massive undertaking. The charge toward standardization is primarily led by the U.S. National Institute of Standards and Technology, or NIST. Back in 2016, NIST kicked off a global competition to find and standardize quantum-resistant algorithms. After years of intense evaluation, we're seeing real progress. As of early 2025, several algorithms have been selected. For encrypting data and establishing secure connections, Crystal's Kyber is a key choice. For digital signatures, which verify authenticity, NIST has picked Crystal's Dilithium, Falcon, and SPIN-CS+. Draft standards are out, and formal publication is expected soon. This will be a huge green light for widespread adoption. NIST is even looking at more algorithms in a fourth round to ensure we have a diverse and robust toolkit. International bodies like ISO and IETF are also working to ensure these new standards work globally. But standardization is just one side of the coin. Implementing PQC presents its own formidable challenges. It's not as simple as swapping out old code for new. First, there's performance. Some PQC algorithms mean larger keys or signatures compared to what we're used to. This can translate to more processing power needed, slower connections, and more data being sent. While the selected algorithms like Kyber and Dilithium are pretty efficient, they can still strain resource-limited devices, like those in the Internet of Things. Then, there's the sheer difficulty of integrating PQC into our existing digital infrastructure. Think about upgrading every piece of software and hardware across countless systems, many of which are old and hard to update. It's a monumental task. Legacy systems are a particular headache. Many organizations will likely use a hybrid approach during the transition, using both a traditional algorithm and a new PQC algorithm together. This provides a safety net, but it also adds complexity and overhead. Figuring out the right hybrid strategy is tricky. We also need to consider developer skills. PQC introduces new mathematical concepts. We need to train engineers to implement these new algorithms correctly, avoiding mistakes that could create new vulnerabilities. It's a steep learning curve. And finally, while these new PQC algorithms are believed to be secure against quantum computers, the field is younger than classical cryptography. Their long-term security is still under intense study. There's always a possibility that new attacks could be discovered, so we need to remain vigilant and adaptable. This transition to post-quantum cryptography is a paradigm shift. It's not just a minor update, it's a fundamental change to how we secure our digital lives. The standardization process is nearing key milestones, but the implementation journey is really just starting. Organizations need to start assessing their systems, identifying where their current cryptography lies, and planning their migration strategy now. The quantum future is approaching, and preparing for it today is essential for a secure tomorrow.